Good evening, students. Today we are going to discuss about the magnetic flux density. From that, we are going to calculate the Maxwell's equation and the magnetic scalar and vector potential. So, in today's lecture, we are going to cover two topics. So, let us start with the first topic, that is the magnetic flux density, and from that, the Maxwell's equation. We have seen in the case of electrostatic that the electric flux density D is equals to epsilon naught E, which is written here. You can see that D is equals to epsilon naught E in free space. The definition is given in the earlier lectures, that how we can write that D is proportional to E, and from that we can write D is equals to epsilon naught E. In the same way, in the case of the magnetic flux density, which is generally denoted by the capital B, we can define. The magnetic flux density B is related to the magnetic field intensity H by the expression 21.1. So B equals to mu naught H. Here mu naught is a constant and it is known as the permeability of the free space. Now this permeability or mu naught is expressed in Henry's per meter, and it has a value that is 4 pi into 10 to the power minus 7 Henry's per meter. So as the magnetic flux density is defined, we can find out the magnetic flux, the total magnetic flux through a surface. That is defined by this expression 21.2, that is total magnetic flux psi equals to the surface integral of B dot ds. So by this equation we can calculate the total magnetic flux coming out through a surface. As this psi is denoted as the total magnetic flux, it is in Webers, and the magnetic flux density is in Webers per meter square, or it is famously known as Tesla. Now we need to know the magnetic flux lines, just like we have seen in the case of electric field, that electric field lines. Here also we are going to understand a magnetic flux line. What is magnetic flux line? Magnetic flux line is a path to which the magnetic flux density P is tangential at every point on the line. Also, in other words, we can say it is a line along which the needle of a magnetic compass will orient itself if placed in the presence of a magnetic field. So let us elaborately understand with an example what is the magnetic flux lines. For example, here we have considered the magnetic flux lines due to a straight long wire, which is shown in this diagram. The flux lines are determined by using the same principle as followed for the electric flux lines. Here the direction of B is taken as the indicated as north by the needle of the magnetic compass. Suppose here this dot, it is the convention that dot with a circle is representing a current carrying conductor through which the current is coming out of the page. So if a current carrying straight conductor is placed here in this at the center of this circle, and if we consider the current coming out from this page, then if we place one needle of a magnetic compass, the north pole of the magnetic compass will give us the direction of the magnetic flux lines. So here you can see that the anti-clockwise direction is representing the magnetic flux lines. Also, from the diagram, we can see that the magnetic flux lines are closed and has no beginning or end. Though from the figure, we can say that this diagram is for the straight current carrying conductor, but it is generally true that the magnetic flux lines are closed and do not cross each other, whatever be the current distribution. So that is important. Whatever be the current distribution, the magnetic flux lines are closed and they do not cross each other. Now we are moving to understand that why it is so, why the magnetic field lines do not cross each other and they are closed. To understand this, we need to again recall the case of the electrostatic. In the case of electrostatics, we have considered the flux passing through a closed surface is same as the charge enclosed by that particular surface. So the total flux psi is equals to the surface integral of d dot ds, that is equals to q enclosed. That we have seen in the case of electrostatic. Now this equation is, from this equation we can understand that the electrostatic charges, that is either it is positive charge or negative charge, it can have the only charge, positive charge or the negative charge. That means it is possible to have an isolated electric charge, which also reveals that the electric flux lines are not necessarily closed. Unlike electric flux lines, magnetic flux lines are always closed upon themselves. Now, why the magnetic flux lines always closed upon themselves? To understand this, we have taken one example. Suppose we have a bar of magnet and we have divided this bar into two pieces. If we divide this bar magnet into two pieces, we have the south pole, north pole in these two pieces. If we further divide these two pieces of magnetic bar, again we will have the north pole and south pole of each of the bars. That means it is not possible to have an isolated magnetic pole by dividing the magnetic bar successively into two. We end up with pieces each having north and south pole. So in a nutshell we can say, we can find it is impossible to separate the north pole from the south pole. So from this explanation we can conclude that an isolated magnetic charge does not exist. So if the isolated magnetic charge does not exist, then the total flux through a closed surface will be equals to 0. That is written in equation 21.4. That is, the closed surface integral of B dot ds equals to 0. Now from this expression we are going to calculate the Maxwell's equation. Before that, we are going to discuss about this expression in 2 or 3 lines. We will discuss here. The equation, this equation means this equation that the surface integral of B dot ds equals to 0 is referred to as the law of conservation of magnetic flux, or Gauss's law for magnetic field, just as that surface integral of d dot ds equals to q enclosed is the Gauss law for electrostatic field. Now another important point from this equation, that is the closed surface integral of B dot ds equals to 0, we can say that the magnetic flux density is conservative in nature, but the magnetic field lines are not conservative. Earlier we have seen that we have derived that magnetic field is not conservative, but from this expression, that is surface integral of B dot D is equals to 0, we can conclude that magnetic flux is conservative in nature. Now, if we apply the divergence theorem in the expression of 21.4, that means in this expression, so we know using the divergence theorem we can relate from the surface integral to the volume integral. So the closed surface integral of B dot ds can be written as the open volume integral of del dot B into dv. So here you can see that expression we have written, the surface integral of B dot ds equals to open volume integral of grad dot B into dv. So that is equals to 0. So from this equation we can have this equation 21.6, that is grad dot B equals to 0. So this equation 21.6 is called the differential form of the Maxwell's equation, and the expression 21.4 is known as the integral form of the Maxwell's equation. So this one is the fourth Maxwell's equation. Now from this expression we can understand that the magnetic field lines are always continuous. So we have studied two Maxwell's equation for the case of electrostatic field. Also we have seen the two Maxwell's equation in the case of magnetostatic. So let us revisit these four Maxwell's equation for the static, electrostatic and the magnetostatic fields. In the first column, the differential form of the Maxwell's are written. In the second column, the integral form of the Maxwell's are written. And in the third column, what are the remarks regarding these math equations. So the first row says that del dot D equals to rho V. It is first we have derived from the Gauss law the first Maxwell's equation, and this one del dot D equals to rho V is the differential form of the Maxwell's equation, and in its integral form will be the closed surface integral d dot ds equals to open volume integral rho v dv. In the second row you can see that just now we have derived that grad dot b equals to 0, or the integral form, that is the closed surface integral of b dot ds equals to 0. From this equation we can say that non-existence of magnetic monopole, that means that it is not possible to have a magnetic monopole. The third row is the del cross E equals to 0, that is the differential form, and closed line integral E dot dl equals to 0, that is the integral form of the Maxwell's equation, and it says that the conservative nature of the electrostatic field. And the last row says that grad cross H equals to Z, that is the differential form, and the closed line integral H dot dl equals to open surface integral J dot ds is the integral form, and that can be derived from the Ampere's law or Ampere's circuit law. From this table it is evident that the vector field is defined. A vector field is defined completely by specifying its curl and its divergence. Or in other way, if a quantity if we take a quantity and if we take the divergence and the curl, and if it follows that particular parameter follows this Maxwell's equation, we can say that either this parameter is the electrostatic field or the magnetostatic field. It is also noted that Maxwell's equations are only for static and the magnetostatic fields. That means here these equations are only for the static fields. That is, either it will be the electrostatic field or the magnetostatic field. Whenever we will study the electromagnetic fields, that means the time varying electric field and the magnetic field, you will see that these first two equations will be remain same, but there will be a change in the last two equations. So we will discuss that one afterwards. So students, we have completed the first topic. Now we are moving to the second topic, that is the magnetic scalar and vector potential. To understand the potential due to the magnetic field, again we will get the idea from the electrostatic. In the electrostatic, we have derived one equation which relates the electric field with the potential, and this is given here. You see that E equals to minus grad V, that is derived in my earlier lectures. So we are going to use the same way, or we can write the magnetic potential in this form. For that, we can define a potential associated with the magnetic field B. But here, I want to tell you one point, that the magnetic potential are two types. One is the scalar magnetic potential, which is denoted by Vm, and the other one is the vector magnetic potential, which is denoted by capital A. Moreover, we should remember that whenever we are going to define this Vm and A, we need to use two important identities. The identities 21.7, that is grad cross grad V equals to 0. We need to use that. That means we need to satisfy this identity, and also we need to satisfy this 21.8, that is grad dot grad cross A equals to 0. Hence, we can say to define Vm and A, we need to know two important identities, that is 21.7 and 21.8, which must always hold for any scalar field and the vector field. So let us start with the scalar magnetic field. As I told you that in the case of electrostatic, we have derived that E is equals to minus grad V. That means this equation shows the potential of the electrostatic field is related to the electric field. In the same way, we can define the magnetic scalar potential Vm, which is in amperes, and this Vm is related to H, and this relation shows that H equals to minus grad Vm, provided this J is equals to 0. Now, why this J equals to 0, this condition must satisfy, we will explain here. To explain this, again we are going to consider the Maxwell's equation, that is grad cross H equals to J. And if we put here H equals to minus grad V or grad Vm, then we can see that del cross H, that means equals to del cross within bracket minus grad Vm. So that is equals to 0. That means the vector identity we need to satisfy. The vector identity is this one, the 21.7. So to satisfy this identity, here H we have considered, that is minus of grad Vm, but it is equals to J, not 0. So to find or to define this H equals to minus grad Vm, we must consider that J equals to 0. So we can say, since Vm must satisfy the condition in equation 21.7, as I told you, that 21.7, hence the magnetic scalar potential Vm is only defined in a region where J equals to 0, as in equation 21.9. So from that we can have one expression of H, that means one expression of Vm, that is the scalar magnetic potential, which is related to the magnetic field intensity. Also, we can note that this Vm satisfies the Laplace equation. Just as we have seen in the case of electrostatic, that the potential V is will satisfy the Laplacian or Laplace equation. Similarly, here we can say grad square Vm equals to 0. Again, the condition is J must be equals to 0. Now moving to the vector magnetic potential. To find out the vector magnetic potential, we are going to use the Maxwell's equation grad dot B equals to 0. So this grad dot B, which we have seen earlier, that the Maxwell's equation which we have derived, and also we need to satisfy this equation 21.8, that is grad cross A equals to 0. Simultaneously we need to satisfy these equations. So if we write that B equals to grad cross A, then these two equations will be satisfied. So here you see that now that is why we have considered the B equals to grad cross A. So here if we put that grad cross A, so grad cross A equals to 0, it is satisfying the equation 21.8. Also it is satisfying del dot B equals to 0, that is the Maxwell's equation. So from that we can define that the magnetic vector potential is related to the magnetic flux density by the expression 21.11. So that is all for today's class, students. We will meet again in the next class. Thank you very much for joining the class. Thank you very much.